In this video, we're going to talk about maximum and minimum values. So first off, we're going to have some definitions. So we're going to let C be a number in the domain D of a function f. And then we have two things here. So if f of c is greater than or equal to f of x for all x in the domain D, then f of c is called a absolute, or sometimes it is called a global maximum. And if f of c is less than or equal to f of x for all x in the domain D, then f of c is called an absolute or global minimum. Now, all we're really saying here is an absolute maximum is the very largest point on a graph, and an absolute minimum is the very smallest point on a graph. So that's all we're really saying here. And so if we look at the following graph, so say we have this graph. Just going to stop there. So in this graph, the very lowest point is all the way down here at 0. So the point 5, 0 is the absolute min. And this point up here, which is 4, 5, this is the absolute max. The very highest point is the absolute max, the very lowest point is the absolute min. Now, one place that confusion sometimes shows up is the absolute max / min value is the y-coordinate. And so the maximum value in this graph is 5, and the minimum value in this graph is 0. Sometimes you're also asked where the max and min occurs at. So the place where the max or min occurs at is the x-coordinate. And now you will be asked to find both of these periodically in calculus classes, and so it's good to know the difference in the vocabulary. So the values, the y-coordinate, where it occurs at is the x-coordinate. So closely related to this idea of an absolute max and min are local max and min. And so the number f of c is called a local maximum value if f of c is greater than or equal to f of x for all x near c. And the number f of c is called a local minimum value if f of c is less than or equal to f of x for all x near c. So now what this is saying is if you just take the points right around the value c, then the very largest point in that interval is a local max if it's bigger than everything else around it, and it's a local min if it's smaller than everything else around it. So let's look at a picture of this situation. And so say we have the following graph. And so this point here is going to be a local min, because if I take everything around it, which to think of taking points around it, just think of like you're taking a corridor or an interval around it. And notice that's the smallest point in that interval that I just drew. So this is a local min. And then this point up here, if you take an interval around it, and it's any interval around it, so you can make it as big or as small as you want, but the smaller, the easier it is to spot things. This is the largest point in that interval, so this is a local max. And then down here, it can be a little hard to tell, but I intentionally tried to draw this a little bit lower than everything else. So this is a local min, because it's the smallest thing around, but if it's also smaller than everything else, and so because of that, this is also going to be an absolute min. And so you can have a local min be an absolute min, and a local max could be an absolute max, but they do not have to be. And so it's possible you just don't have a, you have a local maximum where you don't have a global maximum. Kind of like at this point right here, this is a local min, but it's not the global min. It looks like they're about level, but this point here is supposed to be lower. So one thing about local minimums to be aware of is local max and min values cannot occur at endpoints. In other words, the points to the left and right must be defined. Okay, so you can't have a local min or max at an endpoint. You have to actually be able to go to both sides of it. And we're going to see that in an example. So we're going to look at the following graph now. Point A, point B, point C, point D, point E, and then it keeps going, but we're not going to go any further than that. So what we want to do here is we want to identify local minimums and maximums, just to kind of reiterate this point. So we have a local max, local min, then we're also going to mention the global max and global min. And so first off, this point A. This point A is at an endpoint, so it cannot be a local min or local max. It could possibly be a global min or max, but notice E up here is higher than A, so A is not going to be a global max either, because E is higher than it. And that's actually a good thing to note. E is higher than everything, so the global max is going to be E, and B is lower than everything, so the global min is going to be B. So to find those, you just literally take the highest and lowest points, respectively. Now, for local maximum, B is lower than anything else near it. It's lower than everything, so it's certainly going to be a local min, because it's lower than everything. C is the highest thing around it. If you take an interval around it, you see that it's higher than everything else, but it's not the highest point. So C is going to be a local max, but not a global max. D will be a local min, because it's the lowest point right around it. And E, we already said, is higher than everything else, and so it's higher than the things by it, so E is also going to be a local max. And so here we have our local maxes, will C and E. Our local mins will B and D. Local max is E, and global min is B. And so we can see all that just from this graph. So now let's look at another example. So we're going to look at the graph of f of x equals 3x to the fourth minus 16x cubed plus 18x squared on the interval -1 to 4. Now I'm going to actually draw this graph of this function. It is kind of hard to draw the graph of, but we're going to use technology technically was used to find this graph. So we have a point up here, then 1, 2, 3, 4. Okay, and so this is the graph of 3x to the fourth minus 16x cubed plus 18x squared. And I'll label these points. This is -137. This is 1, 5. This is 3, -27. And then the point at 4 is not going to really be relevant for its coordinate. So from this graph, notice that the highest point on the whole interval is the point -1, 37. And so there is a global max at x equals -1. And the global max value is 37. So remember, where it occurs at is the x-coordinate. The value is the y-coordinate. And so that's kind of the point of why I wanted to do actual points here. Now, 1, 5 is going to be a local max. Well, -137 can't be a local max because it's at an endpoint. But 1, 5 is a local max, and so we have a local max at x equals 1, a local max value of 5. And then 3, -27 is the lowest point, so we have a global min at x equals 3, and a global min value equal to -27. And so this is just kind of to reiterate that vocabulary that we were mentioning before. Now, not all functions necessarily have local minimums and maximums. So for instance, if we look at the graph of f of x equals x squared, its graph looks like the following. Now this function clearly has a global and local min at 0 with a value of 0, but it doesn't have any local maximums or global maximums. It's only got that minimum. So you may not have both. You may only have maximums or may only have minimums. Another example is the function x cubed. If you draw the graph of x cubed, it looks something like the following. And notice there is no minimums or maximums in x cubed. So you may just not have any. And so it's important to be aware you may or may not actually have minimums and maximums. And you may have any mixture of them. You may have minimums and not maximums, or maximums and not minimums, or none of them. Now, one thing you may have noticed is in the graph of a function, its local max and min value, max and min occur at places where the tangent line is horizontal. Okay, so this is something you may have noticed, you may have not noticed it, but when we draw these graphs, the tangent line is going to be horizontal at these places where we have local minimums and maximums. And this is in fact always the case. And so we have the following fact. This is called Fermat's theorem. So if f has a local max or a local min at C, meaning the x-coordinate is C, and f prime of C exists, then f prime of C is 0. So if we have a local min or max at a point, and the derivative exists at that point, then the derivative must be 0, which is what we're seeing here. Those points where the derivative existed, at a local min or max, the derivative was 0 at. Now, one thing to be careful of is just because the derivative is 0 somewhere does not mean there is a max or min there. So, for instance, f of x being equal to x cubed, we have that f prime of x equals 3x squared. So at x equals 0, f prime of 0 is 0. But x equals 0 is not a local max or min. We saw that a second ago. We just drew its picture. So even though the derivative was 0 at 0, that doesn't actually mean we got a local maximum. So you do have to actually have this knowledge that the local maximum in there. Just knowing the derivative is 0 is not enough. Additionally, if we look at the function f of x equals the absolute value of x, its graph is as follows. And so this point, 0, 0, this is going to be a local and global min. So we have a local and global min at 0, 0, but if you recall the derivative of this function, it's 1 if x is greater than 0 and negative 1 if x is less than 0, and the derivative is not defined at 0. And so we have a local and global minimum at 0, but the function's derivative does not exist there. And so it's possible that we have the situation where the derivative does not exist at a point as well. And so those are kind of two things to be aware of. The derivative could be 0 there, but that doesn't mean you have a min or max. And just because the derivative doesn't exist there, doesn't mean you can't have a min or max there either. So despite this, the following is true though. If f has a local max or min at C, then either f prime of C equals 0 or f prime of C does not exist. So if you have a local min or max at a point, then the derivative is either 0 there or the derivative does not exist. Meaning that if we're looking for local minimums and maximums, we only need to check the points where the derivative is 0 or does not exist. And we have a name for such points. And so a critical number of a function f is a number in the domain of f such that either f prime of C, I should have said it's a number C, so either f prime of C equals 0 or f prime of C does not exist. F prime of C does not exist. And so critical numbers are all of the places where we potentially have a local minimum or maximum. They're the places where either the derivative does not exist there or the derivative is 0 there. And so let's look at some examples of computing critical numbers. And so we want to find the critical numbers for the following. So first we're going to look at the function f of x equals 6x cubed minus 14x squared minus 3. So we want to find all of its critical numbers. The first thing to be aware of is this function's domain is all real numbers. And so any place where the derivative does not exist or is 0 will be a critical number. That's an important thing to be aware of. You do have to be in the domain of f. And our next example will actually bring that up. But we've got this function, so we want its derivative now. So the derivative of this function is 18x squared minus 28x, which factors as 2x times 9x minus 14. Now, this is going to exist for all x. This is a polynomial, so the derivative exists everywhere. So the critical numbers are where f prime of x equals 0. So I'll write that down, the critical numbers where f prime of x equals 0. So in other words, when 2x times 9x minus 14 equals 0. Well, this occurs when 2x equals 0 or 9x minus 14 equals 0. If 2x equals 0, x is 0. And if 9x minus 14 equals 0, then 9x equals 14, where x equals 14 over 9. And so those are then our critical points. So the critical points, the critical numbers or points, they're called both, are x equals 0 and 14 over 9. And so those are critical numbers. They're the places where we could have a local min or max. You'd actually need to do some testing, which we will talk about in the future, how to do that testing at these points. But those are places where we could have a local min or max. Next, we want to look at the function g of x equals x to the 3/5 times 4 minus x. So once again, this function is going to be defined everywhere. It's just equal to 4x to the 3/5 minus x to the 8/5. Just if you multiply it out. And so we know that this function is going to be defined everywhere. So that means the places where the derivative does not exist or is 0 are critical numbers. So we're going to take our derivative. And so we have that the derivative of this function is going to be 4 times 3/5 x to the minus 2/5. So we have to subtract 1 from the exponent. Minus 8/5 x to the 3/5. And so bring down the exponent, subtract 1 from it. So this gives us 12 over 5 x to the minus 2/5 minus 8 over 5 x to the 3/5. So we've got 12x to the 2/5, negative 2/5 minus 8x to the 3/5 divided by 5. So this is then the derivative. But we want to know when this is 0 or not defined. So it's going to be easier if we rewrite it by unmixing the numerator. By unmixing it, I mean getting rid of the negative exponent we have in the numerator. So we've got g prime equals 12x to the minus 2/5 minus 8x to the 3/5 divided by 5. And I'm going to multiply the top and the bottom by x to the 2/5. And that's to get rid of the negative 2/5 on the 12. Multiplying this out, we're going to get 12 minus 8x to the 3/5 plus 2/5 is just going to be x. So we have 12 minus 8x over 5x to the 2/5. And so this then is our derivative, and it's easier to see where this does not exist and where it's 0 than the original one is. So that's why we multiplied by x to the 2/5 on the top and bottom. And so now the critical points are points where this is either 0 or does not exist. So for this to be 0, the numerator must be 0. So we have when 12 minus 8x equals 0, then 8x equals 12, or x equals 12 over 8. And 12 over 8 is 3/2. So this function will be 0 at x equals 3/2. But notice that when 5x to the 2/5 equals 0, this function does not exist. So the derivative doesn't exist when 5x to the 2/5 equals 0, and this is when x equals 0. And so that's the only place 5x to the 2/5 equals 0. And so x equals 0 is a place where the derivative does not exist. But the original function did exist at 0. Remember, it existed everywhere. And so this is also a critical point. And so our critical points, in this case, critical points or critical numbers, are x equals 0 and 3/2. And so if the function is defined somewhere, it could be a critical number. And we saw here that it was defined at 0, but the derivative was not, so that gave us our critical number there.